Hello group. This lesson is a follow-up to an investigation we did in class where we investigated specifically the properties of ionic and molecular compounds. This activity was done with slightly different compounds, but this page here that you see before you is just a summary of both the question and the results for a similar investigation. And in this case, solubility, conductivity, as well as general appearance, hardness, odor, things like that were looked at. And we came to certain conclusions that allowed us to categorize compounds based on their physical properties. So at this point, we want to sum up with some of the key properties for ionic compounds in this section. So I'm going to go through this slide here and just reveal some points about ionic compounds and ionic bonding for this lesson. Now, we did observe for sure the hardness of ionic compounds was unique. Generally, they are brittle. If we know their chemical formula, we can observe that they're made up of metal and nonmetal ions, and they're formed by a transfer of electrons between two or more atoms. Second point here is that when that transfer of electrons occurs, it creates charge particles, and the result is a strong electrostatic force of attraction between these oppositely charged ions. That is what we call an ionic bond. I'm going to just show you the visual here of the formation of sodium chloride. Here we have the Bohr diagram for sodium and chlorine atoms. So we have the transfer electrons shown using the arrow, and the result are two charged particles. You'll notice the square brackets around the Bohr diagram. We're going to use a similar notation or format for Lewis symbols in this lesson as well. And then you'll notice also the superscript in the top corner indicates also the charge of the ions. That's how we can indicate that the particles are now charged. I'm going to just show a quick little video clip here to give you a little bit more insight into how this occurs as well.
Such as sodium may lose electrons and become positively charged ions. Other atoms, such as chlorine, may gain electrons and become negatively charged ions. Depending upon their surroundings, the opposite charged ions may attract each other, thus forming an ionic bond.
Ionic compound. No electric current can pass between them. The bulb does not light. If the ionic compound is melted, however, the ions in the liquid can move between the electrodes, carrying charge and lighting the bulb.
Screen. So the next point we want to look at here, then this is kind of a theoretical idea as well, but the nature of ionic compound is different and unique from molecular compounds. They exist as a lattice, a crystal lattice it's called, and this lattice is a network of ions of a specific arrangement. It has a unique geometric shape, and so when we refer to the way in which ions arrange themselves, we call it a crystal lattice, not a molecule. And again, I'm just going to show another clip here just to help you see what this might look like.
Crystal of potassium bromide has a distinctive shape with perpendicular edges. This shape directly reflects the arrangement of the ions in the crystal lattice. The compound is composed of alternating potassium ions and bromide ions.
Okay, the next point is just a bit of a follow-up to the last. When you saw the crystal lattice, you'll notice that there were a certain number of potassium ions and a certain number of bromide ions. And when we refer to an ionic compound, we don't refer to it as a molecule, as a separate particle. We really refer to the lowest ratio of bonded ions, and that's what's called a formula unit. So we can think of it as a unit, and the unit itself, MgCl2, is also a chemical formula, so that's why it's called formula unit, and it is used to represent, again, that smallest ratio of bonded ions. So MgCl2, there would be one magnesium 2+ ion for every 2 Cl negative chloride ions. Okay, this video clip here will just show a simulation of a reaction between zinc and sulfur, and it asks a question at the end which we can try to answer using this idea of a formula unit.
Metallic zinc is mixed with powdered sulfur and ignited. A powerful reaction takes place that produces zinc sulfide. a compound containing only sulfur and zinc. How can we determine the formula of the product, a compound of zinc and sulfur?
So let's think about that question. If we had the reaction equation, and we know that zinc is elemental and it's a solid, and sulfur, we may remember, is octahedral and is also solid. And then we would look at the reaction equation and we look at the product, which is zinc sulfide. Now, to write the chemical formula for zinc sulfide, we need to know the charges on each ion. So zinc forms 2+ ions based on its location on the periodic table. And the sulfur, which is a group 6, forms 2 negative ions. So because of the balance of charges there, the number of ions in this case will be 2 in total for the formula unit, and it will be ZnS. Okay. In that case, this is the formula unit right here, and the subscripts are not necessary because there are only one of each ion. It's also a solid. You saw the chemical reaction, and then the balancing of it would also be necessary, so we can go and add our coefficients to make it obey the law of conservation of mass. So again, there's another example of a formula unit. All right, the fifth point that needs to be made here relates to conductivity of solutions. So we looked at the conductivity, we looked at the solubility, and we saw that some compounds, when dissolved in water, distilled water, had conductance and some had no conductance. And that allowed us to conclude that some formed ions when the compound dissolved, and others, though they may have dissolved, did not form ions. And so the electrical conductivity of a solution is unique to ionic compounds, and also acids. Some acids exhibit this behavior as well. Substances that do conduct an electrical current are called electrolytes, and it's a little bit of a spectrum everywhere from strong electrolytes with strong conductivities through weak electrolytes to non-electrolytes. And this occurs due to dissociation. Dissociation is a term here that is illustrated by the reaction equation. Magnesium chloride solid breaking up into magnesium ions and 2 chloride ions. That's a dissociation reaction equation, and it illustrates why the compound magnesium chloride would in fact have conductivity. So I'm going to show you a few video clips on this just to help you understand this concept of electrolytes.
Strong electrolyte is a compound that ionizes completely in solution. Hydrogen chloride breaks into hydrogen and chlorine ions.
Okay, so this little clip here is showing what weak electrolytes might look like in solution. This particular compound is acetic acid.
Electrolyte is a compound that only partially ionizes in solution. Some hydrogen ions dissociate from acetic acid molecules, but others may rebond at the same time.
Okay, so this clip here is going to show a molecular compound. This particular one would have chemical formula C2H6O, and it's an alcohol called ethanol.
Some compounds that dissolve in water, such as ethanol, do not dissociate into ions at all. Such compounds are called non-electrolytes.
All right, the last point on this slide just sums up an idea that has been presented in grade 10 science, which is that in order to ionize an atom, whether it be a metal or non-metal element, needs to achieve a full valence set of electrons. And for most atoms, we refer to that as a stable octet, or 8 valence electrons. Some of the exceptions would be hydrogen and helium, which are looking to fill their first valence orbit, which has only 2 electrons. So that would not be a stable octet. But the majority of elements that we represent in this chemistry course, we will use that as a target value. Okay, so we're going to look at the Bohr diagrams of some elements and examine how we predict the charge, which is really important if we want to come up with the formula unit. Okay. All right, so we're going to kind of wrap this concept of ion charge together with something else. And this is not new probably to some of you, the use of a Lewis symbol diagram. The Bohr diagram and the Bohr-Rutherford diagrams are part of the curriculum in grade 10, and the Lewis symbol becomes more important and more useful when we want to represent chemical reactions in this course, because really the only electrons that are of interest to us for reactions are the valence electrons. And you'll see here in this chart, which I got from the Hyperphysics webpage, are shown in red. Okay, so all of the electrons are dots, and no nuclear information is shown. So these would be Bohr diagrams for the first 18 elements. And you will also see some headings here at the top which more or less match the numbers that you'll see at the top of your periodic table. There's a bit of a gap missing between beryllium and boron, where there's a whole bunch of elements that are omitted. But here, we're really looking at groups 1, 2, and then 3 through 8 for the first 3 periods. So hydrogen to argon are shown. The Bohr diagrams, again, valence electrons in red. And one of the practice questions in the textbook, which is relevant here, asks us to predict the charge on the most stable ion formed by each of the following elements, and to indicate the ion by writing the symbol, complete with its charge. So this is a good opportunity for you to look at the question. Again, it's on page 71 of the 3U textbook. Pause the video, try to complete these 9 Lewis symbols. And again, what we're showing here are just the valence electrons as dots and the symbol of the element. I'm going to show the first couple just to get you started, and then you can take over with the other ones and then compare to my answers. All right, so how do we do this? First thing we're going to do is write the symbol of the element. So sulfur is S. Sulfur has 16 electrons. However, it only has 6 valence electrons. So I'm going to represent the 6 valence electrons of sulfur in this case, red. Okay, and there they are. Okay, usually we pair up electrons as we fill the 4 sides of the element symbol. And now as an ion, the closest noble gas is usually important to take note of. So the octet rule here, we have 6 valence electrons, 8 is stability. So we're going to add in 2 more. I'm just going to indicate these with a blue X just to distinguish electrons that were present before from those that were obtained through ionization. So 2 electrons are brought into the sulfur atom, and now this becomes a sulfur ion. Put a square bracket around it, and I'm going to put the charge in the top right corner, and that would be the sulfur ion. So I would predict a charge of -2. For barium, barium is towards the bottom of the alkali earth metals. It's element number 56, has a lot of electrons, but because we know that it's going to have the same electronic structure as other group 2 elements, which have 2 valence electrons like beryllium and magnesium, we can predict the charge on barium quite easily. So barium here has 2 valence electrons. Now, when we look at metals, the stable octet still applies. However, gaining 6 electrons is a difficult thing to do. There's a lot of energy involved in that. A much easier and lower energy process would be the loss of 2 valence electrons from the barium atom. So really what we do when we represent the ion for a metal atom is we remove the outermost valence electrons. We write the symbol again, put the square bracket around it, and indicate the charge. So no valence electrons are shown for metal atoms. Okay, so I want you to pause, try to complete the other ones, and come back and check your answer. All right, so here's the set completed. Doesn't take too long once you get the number of valence electrons and you understand that you're trying to achieve stability through a full octet typically. And in the examples that remained, they were all full octet. So we have bromide ion requires 1 additional electron from a bromine atom, so -1 would be the predicted charge. Similarly with chloride, formed from a chlorine atom, it's in the same chemical group, the halogen, so it also would form a -1 charge. Calcium potassium, rubidium, and beryllium ions. Again, no valence electrons shown in the Lewis symbol here. And the charges are indicated, and I just wrote below how many electrons would be lost in each case, because again, we're not representing valence electrons for metal ions. Phosphorus gains 3 electrons. It's in group 5 like nitrogen, and they're shown there, so the predicted charge for a phosphide ion would be -3. All right, moving along here. Now, what else can we do with Lewis symbols? Well, Lewis symbols can be used to represent not just an atom or an ion. That's pretty straightforward, but we might want to use them to represent how a chemical reaction takes place. So it's another way of visually showing something which is very difficult to observe. Okay, atoms are very small. Electrons themselves can't be seen, but we do know that there's trends in the periodic table, and from those trends we understand that the number of particles in elements is known very accurately, and there's no disputing the fact that valence electrons exist and that the numbers match the atomic number on the periodic table. So when we want to illustrate the formation, again, we can write the Lewis symbol for a sodium atom and a phosphorus atom, again showing valence electrons with a red dot. And here it's sort of like a balanced reaction equation. We would need 3 sodium atoms, 1 phosphorus atom, and the result would be sodium phosphide. Now, something seems to be missing here, and I'm not sure where it went, but I'm going to bring in 1 more sodium ion, and I'm going to put the charge +1 on the other 2 so it's consistent, and that would be the illustration of formation of sodium phosphide. That would be the name of it, and on the right side we more or less have a cluster of ions surrounding the central negative ion called the anion, and this would have chemical formula Na3P. That would be the formula unit for sodium phosphide. Okay, it's not a molecule, but in the crystal lattice of sodium phosphide we would have 3 sodium ions for every phosphide ion, and it would have a unique shape, likely quite different than potassium bromide. All right, sodium phosphide. Okay, so just to throw a little bit of nomenclature in there. All right, the next example is to practice doing the same thing for magnesium chloride. Illustrate the formation of this ionic compound. Again, pause the video, work it out, and compare your answer. All right, initially I just set up 1 atom for the magnesium and 2 for the chlorine. Now, if you're not sure how many you're going to need, what you need to remember though is that magnesium as a metal atom is going to lose 2 valence electrons to form a stable ion. Now, to lose 2 valence electrons is one thing, but where will those electrons go? Well, 2 electrons need to be transferred, and in this case each chlorine atom only requires 1 electron. So we can show a simple transfer of electrons here, sort of using an arrow to show this visually, and that's why I drew 2 chlorine atoms, because I would have tried to balance the number of electrons being transferred to the number that are being received. Okay, so the nonmetal atom receives them, and the result is going to be, again, a magnesium ion, and there's no difference in the name between a metal atom and its ion, still called a magnesium. Chloride, again, now is the result rather than chlorine. All right, so this completes the formation of magnesium chloride, and again here I just decided to show the 2 valence electrons that were transferred from magnesium using that blue X as we did before, just to distinguish the electrons that were there initially and those that were there from the transfer. Again, this is just a visual representation. As far as a reaction equation, you would want to write the formula unit for your compound. You would count the number of ions of each element, and you do the same thing as before on the left side. In this case, chlorine exists as a diatomic molecule, so it would be Cl2 as opposed to 2Cl. All right, that's pretty much it for today's lesson. The assigned work we'll look at in the next couple days, and just take note that the content for the 4C is a little bit different as far as the assigned work.